Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do on discrete element method. So right now on my screen what you see is a spherical some sand particles under the gravity is falling on a floor, and discrete element method people are using in different areas where you have particles movement and then particle to particle interaction. You have a lot of things where these are used. So right now you see this, even with a particle to particle there is interaction, particle to floor is there interaction, and you have a number of variety where you can use like a sand particle movement or material handling. Then you have a lot of foods, nuts, where you have particle to particle interaction. It is a bit advanced method. So today is an introductory video. It will be a fun video just to understand how we can do a discrete element modeling within Abaqus. Now we are not going to catch a lot of theory. It will be mainly how we can model it. It's not straightforward. It's a bit use of Python script, and then you have to put some command. So we are going to use Abaqus 6.14-5. With Abaqus 6.16 there are a lot of advancement in terms of discrete elements. So you can use particle modulus, also you can use Hertz contact. We have some limitation with lower version like 6.14, but we'll just try to cover what we did. So right now on my screen you see is a bunch of particles. It's a spherical sand particle. We are just having a free flow fall under the gravity and just looking into how we can model this. So this is a problem we are going to model. So let me start with a new. So quickly I'll just go through the presentation. It will be a discrete element method in Abaqus. It will be very introductory video. So actually we are going to model a floor. We can have spherical sand particle. It will be a solid mesh to start with. So to start with, you have a rigid floor, then you have sand particle, and then the typical method how you can use, you just build a model, you mesh DM particle with a solid mesh, then you have to we have to convert this solid to DM conversion. So there is a script called solid to DM Python script. The script will call using Abaqus command Python, then will give solid to DM Python script -inp, and then you give input file and then give a part file. So it will convert all this solid into DM particle. Then you have to use textpad or notepad, and then in that you have to convert copy paste of this particle, remove solid particle, and then you have to give a section definition. So discrete section definition where you give density, mass related damping, and then you give what is the spherical radius, and then for floor to particle contacts you can have friction like 0.35, but particle to particle we have limitation with 6.14, but 6.16 you can use a Hertz contact theory also. We cannot use Hertz contact theory with 6.14. So 6.14 you have star surface behavior, pressure or closure linear, and then you have to give a contact stiffness. So I just calculate this contact stiffness with trial and error. So we are going to do this. Now in this problem what we are going to do, it's like a rigid floor and the sand particles. So everything is the rigid. So there is no deformable element to calculate what is the time step. So what we are going to use, star dynamic explicit direct user control we are going to use, and we are going to specify what is a minimum time increment. Now along with this we have to use like a contact control assignment, like a rotational term structure, and then we are going to give a contact inclusion like DM to DM, so particle to particle contact, and then particle to floor contact. And then particle to particle contact we are going to use this the contact stiffness, friction, and pressure over closure is like a linear. So for 6.16 you have Hertz, and then you can lot of things we can do, but 6.14 you can use linear pressure over closure linear, and then you give a contact stiffness. Now for DM2 master it is a straightforward. So you are going to use typical friction what we have, and then the final DM file will be ready. So bit here and there, but it will be good learning for you. It will be introductory video. So I already done. So first I'll just create a floor. So we are going to go shell, planar, rigid, and this will be a floor, rigid floor. So approximately I'm taking like 1000 size. So I always put 0, 0. One minute, I think something 0, 0, xy 0, 0, and then I'll put minus 500, minus 500, 500, 500. So almost I get end to end. Then I just put this. So it's a rigid. So rigid we are done. We don't have to define any metal property or section property, but we want a reference point which we are going to use as a end caster condition. So property, we go to property, we'll go to tool, and then at 0, 0, 0 we'll put a reference point. So that way our floor is created. Now we'll create a particles. So particle will be solid. So we are going to have a circular 50 millimeter and then 100 millimeter in length. So we'll say solid. We are going to extrude it. So we need to cut 250. So part will be, this will be particles. Now particles, we have to just give a name particle. We are not giving, we'll make a solid mesh, will not assign any metal property or section property. We'll convert this solid elements into the particle, and then we'll define a section property for this. So it will be deformable, it will be 3D deformable solid extrusion particles, and then we'll give 0, 0, and then we'll just create a circle, and then we'll have this. So already it is 25, and then we'll extrude these by 100. So almost L by D ratio will be 2, and then I'm going to add a, I'm going to use a specific median median theorem to cut this. So I'm going to put xz as 0, and then I'm going to cut this using datum plane. So I'm select and then cut it. So that way we have this. Now what we'll do, we done this. So we'll quickly create assembly. So we'll create assembly. We'll select this and say assembly, and then we'll mesh it. So first we'll mesh floor. So medial axis will use, and then this will be explicit R3D4, and then will this will like a 20 will be good enough, and then we'll mesh it, and then we'll go to the particle. So particle also will use same theorem, medial axis theorem for this type of things. So you get a good mesh, and then this will be like your C3 D8 explicit R. So we are just having mesh this, but we are going to use a different command, and then this will be like a 5. So that way you'll get a good mesh. And then once we mesh it, so the sphere radius, we are going to put half of this. So this is 5, so we are going to put 2.5. So we done that. Now we'll define two types of interaction. Will be first will be P112. We are saying it will be, it's not a contact, we'll go to give a property first. So P12 is a property which will be particles to floor. So we are going to put a penalty friction here, 0.35 for sand, and then we'll create P11. This will be particle to particle interaction. So for that we are going to 1 minute, we have to let me delete this. So tangential, it's a normal behavior, tangential behavior is not there. So it will be P11, contact, and then we'll create a normal behavior. It will be linear normal behavior, and then we are going to add a contact stiffness, which I calculated. It will be 7.54. so you have to play around a little bit here and there to get a contact working. So that's what actually we are given. And then tangential behavior, we are saying penalty based friction 0.35. so that way we define a behavior which will be linear and this, but for 6.61 onwards you have Hertz contact here. So and then tangential we have defined this. So we define that, then we define we have done mesh also. So now we'll define one more thing. We'll create a end caster condition. So we are going to do end caster condition on the so this will be end caster. Now I just want to go to assembly once and then keep this in some panel. So I'm just going to put particle upward by 5 millimeter. So that way you can see there will be no penetration, and then you can see a free fall. So we define that. So I think most of part we are defined. We define the two parts. We define a boundary condition. We put mesh. We also put interaction properties. Now we'll create a step. So it will be like normal dynamic explicit step. So end period we're just keeping 1 second, but it can be shorter one also. And then we'll define a gravity. So we define mesh, everything boundary condition, we created step, and then we'll define a gravity now. So we are defining gravity. It will be in minus z direction. So 0, 0 minus 9810 millimeter per second squared. So that's what actually velocity we are defined. Now I'll just save this as a DM file, and then we'll create a job, and then we'll export it. We'll write an input file, and we are just going to text pad, and then you can see the part floor, and then you see node, then you see R3 D3, and then it's the end of part, and then you see the particles. You have node definition, you have C3 D8R, and then end of part, and then you have assembly. Now one more thing we have missed. We need to create a surface. So floor surface we can create here. So in assembly itself, this is very important step, guys. So be careful here. When you create a master surface for floor, you create in assembly, not create inside the part, because then you'll have issue. So create, and then you say master, and then you select brown as a surface, and then now we'll just export the job. And then once we export it, we'll have a look into how the file looks like. So you see now we have defined a master. Now everything is there. So what we are going to do, we are going to convert this C3D8 into the DM particle. So what we are going to do, we are going to use the command. We have Python script solid to DM dot Python script. So this Python script will convert the solid mesh into DM. Now this is actually Abaqus property. So if you call Abaqus support, they can give you a solid to DM Python script which you can use for the conversion of this. So what we are going to do, we are going to go to the command prompt, go to Abaqus Python solid to DM Python minus sign INP, and then you give input file and you give a minus part. So that way only the solid part is converted. You can give element, different option is there, but this is the straightforward command we can use. So the same what we are going to use. So let me go to the command prompt. Let me go to the our directory, dm tutorial 3, and then you put this command. Now Abaqus solid to minus, and then you give an input file here, dm, and then you put minus part. So once you put this command, you can see it is converted. Now star dm mesh return out in a dm dash dm. So same input file, it will say dm by dm, and then if you take this in textpad or notepad, I prefer textpad. So you see dm pd 3d, this type, discrete element pd 3d, and element set you can see there dm1. Now what we have to do, we have to copy this in a solid where we have this solid mesh command. So I'll just open original file. Now in original file, you know, this is the first one is a floor information, then you have node information for floor, and then you have particle node information. Now we don't want this element, so our file should copy between this star element C3D8R we don't require, and then before end of particle we required this data. So what I generally do, I just go to this, and then I'll just go one more star down command, and then I'll control and I'll do, and then I'll just cut it. So that way it's easy for me to cut and paste, and then I go to upstrace and then element, and then I control and I delete it. So solid definition is gone. Now this is the file which have all dm particle information. So control A and control C, and then you paste this into your original file. So you got all dm definition here, and then you take this your earlier the end of this file's part, and then you just paste it. So it should be start with a star. So this file I'll save as dm2.inp. So you have dm2, it will have star part, and then you already converted this into discrete dm, discrete element method, pd 3d type element, element set dm. Now there are two things we have to do. You have to add a discrete section to this. So I'll just go to, we are going to add this discrete. Now to save the file, I just put this command, and then you paste it here. So before end of part, you have discrete element section, element type, density you have to put. Now I just put a bit heavier density just for fun. This will be just to see rolling, and then have enough rotational stiffness, but you can have your own density. So 2 point, and then alpha is the damping factor based on the mass, so you can have different damping factor what type, and 2.5 is the radius of the sphere. So since we mesh it a 5 millimeter, I take half of that. So you have to generally take half of that or less than that. So 2.5 is the sphere radius. You have this fun, we have put 2.5 density, alpha we have put this. So this way you completed now your discrete. Now I have to already have master surface. I have to create one surface for this. So in assembly, just end of assembly you put enter, and then copy a surface generation. Now it's not a big deal. So you create a star surface name is equal to dm1. So those dm1, and then you already have this instance. So if you see this particles dash 1, you have instance here. So that way you can create the input file for this. So You done that. So nothing fancy here. So we added a surface, so star surface name dm1 and then particle dash 1 dot dm1. So this parts particle dash 1 name you just copy it, and dot dm you keep it, and then that's where surface is generated. So now you have master surface, you have everything. You define this p11 for the particle to particle, p12 is for particles to the float. Now since there is no deformable, so we are going to convert this star explicit comma user control, and then you are going to define this. So I'll just copy that. So star, same thing, you just direct user control and you just put the file there. So same thing, or you put comma direct user control and give this 5.6. Now only thing is we have to define a contact inclusion, and once we've done that, then we are done. So we are going to put inside the step. So star contact control assignment rotational term is equal to structure. You have to put contact inclusion dm to dm. This will be the contact dm to master, and dm to dm it will be p11, and this dm to master it will be p12. So almost we are done. So I think we are ready to submit a run. So let's go and run it then. abq6145j is equal to dm2 CPUs. I just prefer to run with more CPU and interactive. You can also use a double precision by putting double. I think that will be good to have double precision on this command, because you have very high number of particle to particle interaction going on. So let's see how it goes. So run just started, and then we'll just wait for results to get. So it just started. So it's also, the run is also saying to use a double precision, so it's better to use a double precision in this. So we'll just wait for results, and then when the results are out we can discuss. So guys, run is going on. I have some couple of time step results. So what you look is a free flow of the particles. There is also particle to particle interaction, and the particle is just started moving. So this is what example we have done. Is mainly introductory session where you have particle to particle contact, and then particle to particle interactions, particles also interacting with each other. So you need to do something on the contact stiffness, and then if you have 6.16, then you are quite easier. So it was an introductory video. If you like this video, you like this information, don't forget to like us, and don't forget to subscribe us. Thank you. Bye bye.